Now, deletion from max heap. In the prior queue, deletion always occurs at the root node. Okay, so we want to delete the max node all the time. That's why we use max heap. Okay, so let's assume that we delete the root node all the time, which is the largest one. And then after deleting that, then we have to make sure that this should be the max heap again. Okay, so there are two conditions. It should be complete binary tree, and then it should be a max tree too. So here's an idea. First, move after deleting the root node, and then the first thing is to move the last node to the position of the root node. So in this example, in this figure, the 10 is the last node, and then 10 goes up to the root node. Okay, so now this is a complete binary tree, but it's not the max tree. Okay, then we have to adjust. So look at the children. So 15 is the larger one. So 15 is larger than 10, so we swap. And then 14 is larger than 10, then we swap. So now we have the max heap again. And then if we delete one more time, then we delete 15, and then 10 goes up. Okay, and then 14 is larger than 10, so we swap. Okay, that's how we delete. Okay, then here's a question. Okay, after deleting the root node, and then in this figure, what about moving this 15 up to the root node? Would it be okay? Then that's not a good idea. Okay, if we move 15, then it's more complicated than before. Okay, so we cannot come up with a nice simple algorithm with that. Okay, and then also after moving 10 to the root node, then 15 is larger than 10 and 12 is larger than 10. Then which one is the right one to swap? So what if we swap a 10 with a 12? Then it's not as simple, right? So after swapping, then we have to check the 12 and 15. Then 15 is larger than 12, so we have to swap again there. So we have to adjust all the trees if we swap with some small, if we swap 10 with the 12. So when after moving this 10 to the root node, then we have to check the larger child. Okay, and then we have to compare. If the larger child is larger than the parent, then we swap the parent with the larger child. Okay, not just any of them. Okay. Okay, let me try one more time. Previously, we have started talking about max heap and a couple of operations. So basically, max heap looks like this. Okay, so at the bottom of this slide, we have one example of max heap, which is a complete binary tree and the max tree. So the root node has the highest value. Okay, and it is a complete binary tree. Okay, so with this max heap, then we can think of a couple of operations, especially insert and delete. These two operations are important. And as I said in the data structure classes all the time, insert and delete, these two operations are the main operations because that's why we study data structures. Okay, so with the data structures, we will manage the data. To manage, we have to insert and delete. Okay, so there are two problems when we operate on the max heap because the max heap has two constraints. So whenever we do something on the max heap, then we have to keep these constraints. So after insert or delete, the result tree should be complete tree and max tree. Okay, so these two constraints should be preserved all the time. So let's talk about the operations. Now let's talk about insertion into max heap. Basically, we are not going to talk about min heap. Okay, so once you understand how max heap works, then the min heap is kind of straightforward. Okay, So let's assume that we have a max heap. Okay, and then we want to add a new node. Then here's a simple idea, basic idea. First, put the new node at the end of max heap. Okay, and then adjust the tree to satisfy max heap conditions. So let's take a look at this example first. So we have a max heap before insertions. Okay, the leftmost figure is that. Now we want to insert new node. Okay, then first add then node at the end of the max heap. The end of the max heap means since max heap is a complete binary tree, the end of max heap is the left child of node 2. Okay, so node 15 has a right child, and if we have one more node in the complete binary tree, then it should be the left child of node 2. Okay, so we know where to put the new node. Okay, and then we have an implementation of a delete function for max heap. Okay, first, after declaring some integer variables, okay, and first one is to copy the heap 1 to item. So basically, when we delete one node from max heap, all the time we delete the root node. Delete means it's something like a pop. Okay, so we return the root node. So we just copied the root node to item. So at the end of this function, we are going to return the item. Okay, so before returning item, then we have to adjust the max heap. Okay, so after deleting, it is not a max heap anymore, so we have to adjust the tree to be max heap. Okay, next line, heap 1 will be heap index minus minus. By that, we copy the last node to the root, and then at the same time, we decrease the index. So index is the number of elements in the max heap. So we decrease index, but before decreasing, we copy the last node to the root node. Heap 1. Actually, we start from 1. Okay, so we don't use heap 0. Okay, so now the last node is now at the root node, and we don't have last node. So by this statement, now we have the first figure of this slide. So at the bottom of the slide, so now 10 is at the top, okay, at the root node. Now parent is 1. So parent is actually current node. Parent is the index for the current node. Okay, so when we adjust the max heap, all the time we will compare the current node to children. So that's why we use the variable name parent for the current node. So let's go into this while loop. So the while loop statement says the parent times 2 should be less than or equal to index. Okay, index has the number of elements, and parent times 2 is the left child. Okay, so it means if the parent is the leaf node, then we have to quit. Okay, so parent times 2 is larger than index. It means the parent doesn't have a left child. Okay, then we cannot go into this loop. So as long as we are in this loop, then it means at least we have left child. Now, the first if statement, it says if parent times 2 plus 1 is less than or equal to index, then we go into this if block. What does that mean? So parent times 2 plus 1 means the right child, okay? And if the right child is less than or equal to index, it means we have the right child. There is the right child, a right child. Okay. Then if we have a left child and right child, then we have to compare these two children, and we have to find which one is the larger one. Okay. So that's what we do here. If the heap parent times 2 dot key is greater than the parent times 2 plus 1. Okay, it means if the left child is larger than the right child, then the larger is parent times 2. Larger is the left one. Otherwise, larger is parent times 2 plus 1. Okay. Else means we don't have the right child. We have only one left child. Then the larger is obviously just parent times 2. What if we have only a right child without the left child? We cannot have that kind of case because it is a maxive, which means it is a complete binary tree. So if we have a right child, it means it has a left child too, all the time, for sure. So after this if and else statement, larger is the index for the larger child. Okay. If we have only left child, then the larger means the left child. Okay, now in the next if statement, we compare the parent one to the larger one. So if the parent one is, we are talking about the key, okay? So if the parent one is larger than or equal to a larger one, the larger child, then we stop here. Parent is larger than the children, any of the children. So it satisfies the constraint. Otherwise, parent is smaller than the larger one, then we have to swap the parent and the larger one. And then parent is larger, it means we go down. Okay, after swapping, then the parent goes down to the larger one. Okay, and then that's our current node again. And then we go back to the while loop and we do the same thing. If parent times 2 is less than or equal to index, it means parent is now leaf node. Okay, then we do the same thing. And after this while loop, then this tree is maxive again. And then we return the item, which was the root node. That's it. Okay, from the following max heap, delete 3 largest nodes sequentially. Okay, first one, we delete 30, and then 14 should go up. Okay, and then 25 is larger than 20, and 25 is larger than 14, then we have to swap 25 and 14. And now 14 has 2 children, okay, 15 and 10, and 15 is larger than 10, and 15 is larger than 14, and we have to swap. Okay, so now if we look at the leftmost left children from the root node, then we have 25 and 15 and 14. Okay, then next, if we delete, there should be 25, and then the last node is 12, and 12 should go up, and then we have to adjust again, and delete one more time and adjust again. Okay. And a long time ago, we talked about the complexities of insertion and deletion in the max heap. Okay. Then the complexities of heap operations are log n for insertion and deletion. Then why? Okay, think about these algorithms. Okay, when we add one node, then we added that node at the end of the max heap first, and then we checked the ancestors of this node. Then how many ancestors do we have? Log n. Now when we have n nodes, then we have log n ancestors. Think about the depth of this tree. So every time we have 2 children, okay? So if we have one node, the depth is 1, then we have one node. If depth is 2, then we have 3 nodes. And if depth is 3, then so exponentially we can increase the number of nodes as the depth increases, okay? So the depth is actually log n. Okay, so when we insert a new node, then we have to check the ancestors. So from the leaf node, from the last node to the root node, how many nodes do we have? Following this path, basically we have log n. Okay, what about deletion? So basically the same thing. When we delete the root node, then we move the last node to the root node. And then what should we do? We have to compare the children, and then we have to swap if the children is larger than the current one. Okay, so the computation is a little more complicated, but in a big O notations, basically it is log n2 because we can compare 2 children. Okay, that's just constant. Okay, it doesn't matter how long the depth of the tree is. It doesn't matter. We just need the constant time here. Okay, so we have to check the children, and then we go down, and then we check the children, and we go down. So every time we go down, then how many times can we go down? Log n. So basically, this complexity is based on the depth of this tree, and the depth of this tree is log n. Okay, now let's assume that we have a Maxip class with implementations for the functions. Then we can test this class in the main function. Okay, so we declare one Maxip pointer mh, and we allocate memory space, and we have two elements, E1 and E2, and we can insert E1. By the way, E1 is an instance of a structure element, so we assign this key and the data. Okay, then we insert E1. Okay, and then we update this E1 and we insert E1 again. Basically, when we insert new instance, then we copy this structure. Okay, so we copy this structure to an element of an array. Okay, so even with the same variable E1, but still we are inserting new element, and insert another and another, and we can print and we can see the result, and then we can call delete and we can see the result if you want. Okay, and delete and print. Okay, so you can try this Max here with this code.